Hello and welcome to York University's monthly Teletube broadcast, the online astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. We are broadcasting live from the Alumni Carswell Observatory, located at York University in Toronto, Ontario, Canada. York YouTube now broadcasts every last Friday of the month at 7:30 p.m. Eastern Time. For any questions or comments you have of our past shows, or if you have suggestions for future topics, please send us an email at observe@yorku.ca. You can always connect with us on Twitter or Instagram with the handle at York Observatory and Facebook at Alumni Carswell Ops. Good evening, everyone. I am Zena, and I will be one of your hosts this evening along with Maheen, Camilla, and Noor. We're here from the Alumni Carswell Observatory at York University. Tonight, we've got a special guest speaker, Dr. Linsky, who will be talking about solar eclipses. Before we start, I would like to mention that the observatory at York campus is in Toronto, and we would like to welcome you all to our show and to acknowledge the traditional land that our telescope is on. The observatory acknowledges its presence on the traditional territory of many Indigenous nations. The area known as Toronto has been caretaken by the Anishinaabe Nation, the Haudenosaunee Confederacy, the Huron-Wendat, and the Métis. It is now home to many Indigenous peoples. We acknowledge the current treaty holders, the Mississaugas of the Credit Nation, of the Credit First Nation, and we would like to say that our stargazing and astronomical efforts join the long history and current practices of astronomy for this land. The observatory looks forward to continuing to learn and revitalizing our knowledge in this area. I will now hand it over to Noor for the speaker's introduction.
Thank you, Zena. I'll be talking a bit about Dr. Linsky's research. Dr. Linsky, along with his former students and colleagues, conducts groundbreaking research in astrophysics, focusing on analyzing high-resolution stellar spectra, especially in the ultraviolet range. Their work encompasses understanding star and exoplanet atmospheres, probing the interstellar medium, and mapping deuterium abundance in our galaxy. Utilizing data from advanced instruments like the Hubble Space Telescope and others, they've characterized various stellar phenomena, including chromospheres and accretion processes in pre-main sequence stars. Their research also uncovers properties of interstellar gas and its comparison with the outer halosphere and the local cavity. Dr. Linsky has authored Host Stars and Their Effects on Exoplanet Atmospheres, dated 2019, and boasts an impressive publication record with 407 papers. We are incredibly delighted to welcome him as our distinguished guest speaker. Now we will start the presentation.
Hello, my name is Jeffrey Linsky. I'm an astrophysicist at the University of Colorado in Boulder, and I study stars, the sun, and gas between us and nearby stars. What I'd like to do is talk about the eclipse coming up on April 8th of 2024, and talk a bit about what solar eclipses are, what to look for, what you should bring to an eclipse, past eclipses that I've seen, all 13 of them, and I'll talk in detail about the upcoming April 8th eclipse and future eclipse. I might point out that I don't go as a professional astronomer. I go as an amateur to enjoy what's happening. This is one of the great events that nature puts on for us, and it's to be experienced. It's a joyful thing, and I encourage everybody to go and watch it. So, first is, what's the difference between a solar eclipse and a lunar eclipse? Solar eclipse is when the moon comes in front of the sun, and its shadow produces a narrow path, roughly 100 miles wide, thousands of miles long, as it crosses the Earth, due to the fact that the moon is moving relative to the sun. A lunar eclipse doesn't occur at new moon, it occurs at full moon. And since the Earth is so much larger than the moon, the shadow is much wider, and as a result, a lunar eclipse lasts for several hours, whereas at any point on the Earth, a solar eclipse can be seen only for several minutes. So, you might ask, why don't we see a total eclipse of the sun every month? And the answer involves three things actually. Namely, the moon has to be aligned with the sun and the Earth. And if the lunar orbit were parallel to all the other orbits of most of the planets in the solar system, that would occur every month. But in fact, the lunar orbit is inclined by about 15 degrees relative to the sun-Earth direction. So as a result, most of the time, the shadow of the moon misses the Earth. It's either too far north or too far south. And only occasionally, when the moon is actually passing through the sun-Earth line, do we actually see a total eclipse. So the moon has to be aligned in the right place. The moon also has to be close to us. And the reason is, at its average distance, the moon is just about the same angular size as the sun, but the lunar orbit is not a circle, it's an ellipse, and as a result, the moon is sometimes closer than average, in which case it looks slightly larger and totally eclipses the sun. At other times, when it's further away, it's slightly smaller than the sun, so we get what's called an annular eclipse. And finally, you have to be in the right place at the right time. So, this is an example of a lunar orbit showing that it's not a circle, it's slightly elliptical, and the difference between when the moon is closer and further away is actually an important effect. And that's shown here. On the right, you'll see the sun, what the moon looks like when it's closest to the Earth, called perigee, and when it's furthest away from the Earth, called apogee. And you'll notice a significant difference in the size of the moon. And whenever you hear that it's a supermoon, go out and look, because at that time the moon will actually appear to be significantly larger than on average. The sun also the orbit of the Earth around the sun is also not a circle, it's an ellipse, but that's only slightly off. So the difference in angular diameter of the sun is only slightly different depending on the time of year. But if you look at the numbers, you'll see that when the moon is near perigee, it will completely cover the sun. And when the moon is near apogee, it won't completely cover the sun. And then we have the sun during totality will be a bright ring of emission, not totally covered up. So, let's look a little bit at the numbers. The shadow of the moon is only about 380,000 kilometers long. But on average, the moon is 384,000 kilometers. So on average, when the moon is at its average distance, it only just makes the shadow hit the Earth. That's why the shadow is very narrow, and at other times we have an annular eclipse. So what's shown here are the recent annular eclipse in October 2023 and the path of the upcoming total eclipse, April 8th, 2024. And you'll notice that the eclipse lines are relatively thin, are long, and are not west to east. They're, in the case of the annular eclipse, it was northwest to southeast, and in the case of the upcoming total eclipse, it'll be southwest to northeast. And the reason is, during the annular eclipse, the moon was coming down from north, passing through the Earth-Sun line, and then heading south, and that produces the path that you see. And during the total eclipse coming up, it's the reverse. Namely, the moon is coming from the south, passing through the Earth-Sun line and then heading north. Okay, so what's shown in the lower left is a picture of the annular eclipse last October, and you'll see the sun is not completely covered. It's a ring, and that would be called the total annular eclipse. And of course, when you're outside of that narrow path where the moon actually occults the sun, you get a partial. I should point out, a partial phase of the solar eclipse is not interesting. If you didn't know an eclipse was occurring, a partial eclipse that is, you would never know it from the ground because the decrease in the light seen is very small. And the real effects are only when you're in the totality region. So, let's look at what the moon's shadow looks like from space, looking back towards the Earth. And what you see is a dark shadow called the umbra, surrounded by a partial eclipse shadow called the penumbra. And notice that that umbra, that deep shadow, is moving across the Earth at about 2,000 miles per hour. So one of the things I will encourage people to look for is watch that rapidly moving dark shadow as it comes from the southwest, heading right towards you and then moving away towards the northeast. Okay, here's a composite set of pictures of the total eclipse seen in 2006, showing from before eclipse on the left to after eclipse on the right, going through the partial phases. And this is about every 8 minutes between the separate exposures. But I want you to pay attention to what happens just before totality. At that point, the remaining piece of the sun is an arc almost like a straight line, close to a straight line. That will be important. Pay attention to that. Okay, for an annular eclipse, shown here, sequence of photos going left to right on the top line and left to right on the middle line. You'll see at totality, second line near the right, there's that thin annular eclipse line, brightness. Unfortunately, it doesn't get very bright during an annular, it doesn't get very dark during an annular eclipse. So it's not, the sort of things that you see during a total eclipse. So what do you see during a total eclipse? First thing that will immediately hit you is the sun is surrounded by white light. And the white light is from the corona. It's hot gas, million-degree gas. And what you're seeing is reflected sunlight by electrons in the corona. But that white light has structure to it. Sometimes it looks like bar magnet, metal filings. Sometimes it looks like streamers. Sometimes it looks like what are called helmet streamers, which are broad at the base and narrow as they go far away from the sun. And you'll also, even with the naked eye, see what are called prominences. And these are regions of relatively warm gas, typically 10,000 degrees in temperature, magnetically confined, roughly, and look at them and you'll see they are red. And that red is because of the H-alpha line of hydrogen, and elsewhere, the chromosphere, you'll see red produced by hydrogen. Okay, so the corona looks different at different times. When the sun is very active, which is about now, it'll show many streamers in different directions. That's shown on the left. And at other times, when the sun is relatively inactive, it'll almost be closer to a symmetric type shape. Here's some more examples of solar corona during eclipses. On the right, you'll see all that red on the edge. That's the chromosphere. And the emission is due to hydrogen. Here are two other examples showing bright streamers in the corona. Okay, the eclipse path. You look at this figure and you see in the middle where it says 2024, that's the April 8th eclipse that is coming up, passing from Mazatlan, Mexico, through Texas, through mid-America, crossing Buffalo, where I will hopefully see it, and then on into the maritime provinces of Canada. Okay? Compare that now to the eclipse path of 2017, which is the narrow yellow line crossing from Oregon to South Carolina. You notice the eclipse paths have different widths. And the reason is the eclipse in 2017 was where the moon was not quite optimal, a little bit further away than the optimal position. So it was a shorter eclipse. The one in 2024 will be a 3.5 or a 4-minute eclipse, depending on where you are. So it has a wider path. And then you'll see a wide path crossing from California to Florida. And that's the upcoming, I said upcoming, it's coming, August 12th eclipse of 2045. I hope to be able to see that, but I'll be 104 at the time, and who knows. But at any rate, notice its path is much wider, and the reason is the moon is very close to the Earth at that point, so as a result, it's a 6-minute eclipse. Okay, so what to look for? In the bottom, you'll see a picture of what the totality looks like at the very beginning. And what you see are these little, what are called Bailey's beads, areas on the moon between mountains where sunlight is still coming through. And that's just at the very beginning and at the very end of eclipses. The picture above is the so-called diamond effect. And at this point, your eyes are dark adapted, and all of a sudden this bright light comes on as the sun emerges from the moon, and that's called the diamond ring. Okay, then there's a real subtle effect that if the sky is clear and all the conditions are good, you have a chance of seeing. It's a really weird thing. It's called shadow bands, and it is the sort of equivalent to what's to the fact that stars twinkle. If you look out at the night sky, look at stars, the brightness changes very rapidly. And the reason is you have a point source of light shining through a turbulent atmosphere, which is bending the light paths slightly, and as a result, the star looks like it's becoming brighter and fainter very rapidly. Well, imagine what would happen if instead of a point of light, it was instead a line of light. Okay? And as I pointed out before, just before totality and just after totality, the sun is sort of like a line, sort of bent line, a little bit of a crescent. What then happens is that line of light shining through the turbulent atmosphere produces a whole sequence of brighter and fainter lines on the ground that move across very rapidly as if there are a whole bunch of snakes running across the ground. And in order to see this effect, you have to do something that is contrary to everybody's intuition. Namely, just before the eclipse, look down. And not just down at the ground, look at some white thing, a sheet or some shirt or something white that you've placed on the ground, and then you can see this subtle effect of these snakes running across the ground. Okay, so you look up during totality, and what do you see besides the solar corona, which is interesting in itself? If the sky is dark enough, meaning no clouds, you will then see some bright planets. What's shown here is Venus, which will be the most obvious one, will be to the lower right, Jupiter to the upper left. And these should be visible. You don't need binoculars, you don't need any equipment. They should be visible to the naked eye. But there is a special surprise coming up. In addition to those two planets, you should be able, or may be able, to see Mercury, which will be close to the sun. And very few people have seen Mercury because it's hard You have to be at the right place at the right time, but one of those right places and right times is in the middle of a total eclipse. So look for Mercury just a little bit above the sun, and then look over towards Jupiter, and if predictions are right, you will see a comet. It may require binoculars. We can't predict the brightness of comets too accurately, but look towards Jupiter and you may see a comet. Okay, let me give you a little negative thing about eclipses. You want to go to eclipse, you choose the right site, and the unfortunate thing is 1 million people also want to go to the same site at the same time with their cars. So as a result, there almost certainly will be enormous traffic jams, certainly just before eclipses, just after eclipses. So if you want to see a total eclipse, be there the day before. If you want to get there, drive there in the morning of the eclipse, good luck. Okay, and then I saw this diagram figure in the internet about the Great American Traffic Jam. My relatives in Buffalo, New York tell me that the local media are predicting 1 million visitors to Niagara Falls at the time of the eclipse in roughly 500,000 cars, and I assure you there are nowhere near enough parking spaces, either on the Canadian side or the American side together, anywhere near close to 500,000. So that guarantees a total traffic jam. Okay, what to bring? Okay, one of the things you might not think about is a chair, portable chair, because if you're going to be there for the partial phases, that's an hour before and an hour after totality, you might as well bring a chair. And be in an open place, bring blankets if it's cold, bring something to eat or drink, games, food, whatever. Make sure there's a bathroom not too far away. And then I have a number of things that I personally encourage people to bring. One is a white cloth, or to put on the ground, or snow, if it happens to be Buffalo, New York, a kitchen strainer, or anything that has many small holes. And I'll show what a pinhole camera can do when you have something with small holes. Bring a cell phone. Get the app called Totality, and that will tell you where the eclipse will be and what time to be there and how long the duration of totality is. If you're going to take any pictures with your cell phone looking at the sun, make sure you have a dark filter. And if you want to take a picture of the sun with your cell phone during totality, take the dark filter off. Many people ask me about, they want to bring all their professional equipment to take all kinds of photographs during and around eclipse. I don't recommend it. But if you insist, you need telephoto lens, tripod that can drive and follow the sun's path across the sky, dark filters, but not during totality. Take it off. A computer to control the camera, and be prepared to lose valuable time while playing with your camera. I don't know, I can't count the number of times I've heard or people tell me, oh, I set everything up for the eclipse, but I forgot to take the filter off during totality, or I forgot to put the filter back on during the partial phase and destroyed my camera. Oh well, that's why I don't advise it. If you do insist, make sure you rehearse what you're going to do during that 3 to 4 minutes of time of totality, because everything is going to happen very fast. Okay, I suggest a timeline. Okay, think about this. An hour or so before totality, set up at your site, watch the shadows during the partial phases as the sun becomes narrow, it's not a circle, but becomes narrow. The difference between dark and bright at shadows will become smaller and smaller and eventually become almost nothing at all. So you go from very dark to totally bright. Okay? That's a phenomenon you can only see during partial phases. So watch the shadows, take pictures of your surroundings, take pictures of your friends, make partial eclipse images with your hands or kitchen tools, and I'll show that in a minute. About 2 minutes before totality, look to the southwest, and you'll see the rapidly advancing umbral shadow, and it'll be moving. You'll see it moving. Now, some people get scared from it, but it's natural. Note the rapidly decreasing light level. It starts to get cooler. Animals go to sleep. Birds stop chirping. And a little bit of weird type phenomenon. And then 10 to 15 seconds before totality, look down at your white cloth and you'll see the shadow bands running across. At the beginning of totality, take off your eclipse glasses. I know people who didn't and saw nothing. Take off your glasses. Look for Bailey's beads and the red chromosphere at the edge of the solar disk. During totality, look at the corona, of course. You'll see the loops and helmet streamers extending well beyond the edge of the sun. Look for the planets. Maybe you'll even see Mercury and bright stars. Look at the twilight in all directions because you'll be completely surrounded by twilight. You'll see sort of the reddish image of twilight 360 degrees around you. And also, and don't waste time playing with your camera. And just after totality, you'll see the diamond ring, the shadow bands come across again, return of sunlight, put on your eclipse glasses if you look at the sun. And then, very important, after totality, you have to have a party, celebrate, and plan your next eclipse. So, a little bit about things to bring. Eclipse glasses, not normal solar glasses. They aren't good enough. You need eclipse glasses. They're available in many, many places, including supermarkets, hardware stores, whatever. But don't try to get them on the day of the eclipse because they'll all be gone. So let's see. You can make a pinhole camera to look at the partially eclipsed sun. Solar filters. You can buy filters for cameras. They have to be darker filters than what you do for your naked eye because the cameras actually, amplify the sunlight. I mentioned pinhole cameras. Any kind of device that has multiple holes will give you multiple images of the partially eclipsed sun shining on the ground on your white cloth. But you don't need that. Just take your two hands, put them together so you create a small hole, have the sunlight go through the small hole, image on the ground, and there you'll see the partially eclipsed sun. And when you do this, you will amaze everybody around you. Okay, if you're near a tree, just look at what the leaves on a tree do to sunlight, because sometimes the leaves will be close together. That will produce a pinhole camera effect. Look on the ground and you'll see the partially eclipsed sun multiple times. And then I show the example of the two hands making a pinhole camera, giving an image. Okay, so I want to point out the bottom figure there where you see a person holding sunglasses in front of the input for their cell phone camera. Yeah. If you don't do that, you're going to destroy your cell phone. So make sure you protect your cell phone if you're looking at the sun during the partial phases. During totality, take it off and you'll get an image, you'll get a figure, but it won't be a high quality figure like the ones I showed before. Okay. Let's see. Yes. Okay. I've been to 13 eclipses, 12 of them total. And if you want to see eclipse, you have to go to the right place at the right time, and the right place is often at the end of the world. So you'll see a number of places that really are the end of the world. But I want to point out three things. 3 eclipses I saw. Finland, where it says dark cloud, between clouds, and China, where we saw some clouds, and Palm Cove, Australia, between clouds. It often happens that it'll be cloudy before, during the partial phases, and then during totality, things open up. Don't ask me why. I'm not a weather person, but it often happens that, just because it looks like it might be bad conditions beforehand, you'll often see totality. So I've seen a number of total eclipses. The last one I saw was in Albuquerque, New Mexico, which was a partial, and before that, Western Australia, where we traveled halfway around the world to see an eclipse that lasted all of 1 minute and 2 seconds. You have to be a little bit crazy for this. So let me show a few pictures of eclipse sites. This is the eclipse waiting for totality in the eclipse in China, 2009. And, not much happens during the partial phases. So you see people setting up equipment, standing around, talking to each other, sitting, just sort of waiting for the prime event. And since it was not a really clear day, the pictures that people obtained were sort of a little bit cloud covered. Okay, Palm Cove, Australia. Everybody waiting for totality. You look out and you see clouds in the sky. It turns out that at that exact location, we saw a beautiful eclipse, but a mile away in either direction, they saw nothing. That happens. Easter Island, Chile. There you see people setting up eclipse, being watched by that statue, the Moai. And the day before it rained, and during the day, it was absolutely beautiful. Excellent eclipse. Then here's Svalbard, latitude 78.5. Okay, the furthest north place you can fly on a commercial aircraft. And we're sitting out there on the snow, dressed in all of our clothes, because it was pretty cold. And you notice the very long shadows. The sun was low in the sky, and we had to actually be at the right place so the eclipse was not occulted by a mountain. And also, you'll look to the right and you'll see the little sign saying, beware of polar bears. We didn't see any. But there was an image of the sun noticed just above one of the local mountains. And then from the polar regions to the equator, we saw an eclipse in Indonesia, and there they really hyped up the eclipse. Signs and equipment and shirts and all kinds of things advertising the eclipse. And we saw it on the front yard of the Sultan, the local Sultan, shown on the right. And there is, on the left, his family out there watching the partial phases. A site in 2019 eclipse in northwestern Argentina. This is where they set up seats for us, actually, not chairs, but in the distance, the Andes, and it was a beautiful eclipse. So, eclipse paths. Here's shown the eclipses 2021 to 2040. You'll see the annular eclipse of last year going across the southwestern part of the U.S. You see the total eclipse coming up, going from Mazatlan, Mexico, to the Maritimes over Canada, and we'll see it in Buffalo, New York. And you also see some other eclipses. There's the eclipse coming down from the top, you see in blue, total eclipse, and we're planning to see that in Iceland. And then there is a path going across North Africa, the eclipse in 2027, that hopefully we'll see in front of the pyramids in Luxor, Egypt. The path going through the Great Lakes area in April 8th will cut across Cleveland, Buffalo, Rochester, and heading east. You'll see it's 3 minutes and 44 seconds, and hopefully we'll get all of it. People who are just outside of the totality zone, like Toronto and Detroit, you better head south, otherwise you won't see totality. 2041 to 2060, there'll be more eclipses, and you'll see cutting across the U.S. in 2045, April 12th, will be this eclipse that I hope to see when I'm 104. So that's all I need to say. I just want to mention eclipses have provided major scientific discoveries. They will in the future. I'm not going to eclipses for that purpose. I'm going there to enjoy it, and I hope that all of you have the opportunity to see at least the April 8th eclipse coming up, or any future eclipse. You need to see at least one of them in your lifetime, and once you've seen one, you may become an eclipse junkie like me. Thank you.
Great thanks to our guest speaker, Dr. Linsky. He is fortunately able to be live with us tonight for questions. It was an amazing talk, Professor, and we thoroughly enjoyed it. I will now hand it over to my colleagues for some questions.
That was an amazing presentation, Professor. I have a quick question. How do scientists predict eclipses?
Good question. The way we predict eclipses, and by the way, I'm not somebody who does eclipse predictions, but the experts are people who know or have measured accurately the orbits of the Earth around the sun and the moon around the Earth. And these orbits are known to extremely high precision, which is why we can predict the timing of an eclipse to a second and its location to within a fraction of a kilometer. We actually are able to predict eclipses going back several thousand years in time or thousands of years in the future. And actually this ability to predict past eclipses has been useful for historical reasons. It's a very good way of timing events in history.
That's really interesting. I didn't know that. Thank you.
I also have one question. Thank you for the wonderful presentation. Also, I appreciated you encouraging people to enjoy the eclipse instead of fiddling with their cameras and missing it. But my question is, I was curious, you mentioned about a comet being visible. So what comet is that? And is it safe to use aids such as binoculars or telescopes to try to catch it?
Okay, first of all, comets, if they're bright, are naked eye objects. You can easily see them with no equipment whatsoever. They're not too bright to look at with your eyes. They're usually a little bit dimmer than what can be seen with the naked eye. So a binocular would help. Binoculars would help on that. But predicting the brightness of comets is, shall we say, an art more than a science. And there are predictions, and then we're off by factors of 100 in terms of too bright or too faint. So we know the comet's going to be there, but we don't know really how bright it's going to be. So my guess is bring along binoculars and look in the direction of Jupiter, and you may see it.
Thank you so much.
Thank you again, Professor. I wanted to ask regarding solar eclipses and the impact of wildlife and the natural environment around them. Do you have any comments to say regarding that?
Yes. What I've seen is animals, birds, whatever, think that night is coming. So, they go into their nightly, environment. Certainly, what's very obvious is birds will become very quiet. They really think it's, nighttime. At an eclipse that I saw in Jackson, Wyoming, we're looking out, and just, before eclipse, the moose. Oh yeah, there are moose who sort of came out and walked over to where there was water, thinking, well, it's the time for their last drink before nightfall. And they were surprised because night didn't come All of a sudden it was very bright and then they disappeared.
Thank you so much, Professor.
All right. Well, everyone, you have been listening to the Allen I. Carswell Observatory's monthly Teletube broadcast, the astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. Thanks to Dr. Linsky for being our guest for tonight and educating us regarding the upcoming April 8th eclipse and solar eclipses in general. The hosts this evening have been Zena, Noor, Cam, and myself, Maheen. All of our programs are free, but if you would like to make a donation, see our website at yorku.ca/science/observatory. You can always connect with us on Twitter with the handle at York Observatory and check out our website for show notes, content, updates, and contact info at yorku.ca/science/observatory.